Assalamu alaikum wa rahmatullah. So we'll continue with our quadratic optimum regulator systems. So whatever theory you have covered in the last class is basically a system of the regulated system. In the regulated system, there is no input. Rather, we customize the input in such a way that it regulates the system's behavior. So basically, here you is the input, which is obtained by taking the feedback of your state with the gain minus k. Our system represented by x dot equal to ax. And our x dot equal to ax plus pu is our system. So now here, this is your feedback gain, and somehow you're choosing the feedback gain in not an ordinary way like in the pole placement method, rather with a particular cost function. We are trying to figure out our uh, gain matrix K. Okay, so this is your cost function. We will elaborately explain that, and this is also a quadratic nature. That means the highest order of this system will be of the second order. It may or may not have first order as well. So, but we keep it simple. Only the square terms are available here. Okay. So, and based on this optimization or cost function, we figure out our ultimate objective is to figure out the input U with not arbitrary gain k, rather the gain will be chosen in such a way that we can have an optimal control input. So this is your optimal control input. We'll just review. We already have discussed all this in the last class. And the k is chosen in such a way that it will have a pattern like this. Okay, so R is the weight matrix for your energy input, and P is a semi-definite matrix. Ultimately, our objective is to find out the matrix P from the reduced matrix Ricardo equation, which is given here. So ultimately, based on this equation, most of the parameters are known except P. So we have to find a suitable value of the P matrix that will be used to obtain the optimized K matrix, and based on that, you have to find an optimal gain K. So this is the procedure basically. So now, today we're going to solve example 10.9 using this method that we have just explained. So a system is given 10.9, example 10.9. So regulator system. So there is, say this is a second order system with T integrator in the middle. So from the system, sometimes equation may be given, sometimes it won't be given, but from the system, we will be able to figure it out. So that is why I'm just assuming that they haven't given you the system matrix and B matrix. Rather, we are just trying to figure it from the diagram. So now let's see how it becomes. So from each of the phase, the signal will be going to the gain matrix. Then from the gain matrix, it will be going to the input. So this will be your input U, and this will be your X1. The diagram will be given, so maybe the equations will not be given. So you have to figure out. So similarly, you can say that this is also x1 dot, because after the integration, this is what we are going to get, and this will be your ultimately x2 dot. So now from this given system, we can write the equation as x1 dot equal to x2 x1 dot equal to x2 and x2 dot equal to x2 dot equal to u. So it's a very simple system. So based on this, we can write that x dot, which is nothing but x1 dot and x2 dot, is basically a matrix, and which is obtained from 0, 1, 0, 1. There is no 1 involved, so 0, 0. And your matrix, the vector is x1, x2 equal to, no, there is a U matrix as well. So plus 0, 1 U. So from this one, we can see that our system's A matrix is this, and this is our B matrix, which will be required for your reduced matrix Ricardi equation. As you can see here, A, B, okay, as well as R and Q will be required. So objective function in general is provided in the problem. So the part of the problem is your J is given. So we haven't yet started solving the problem, just we're discussing the question so far. So 0 to infinity, X transpose or X transpose QT, QX plus U square dt. So as you can see, the Q is not given. So, but sorry, R is not given. Q is given. So what they have said that Q is of this nature, 1, 0, 0 mu, where they have kept the mu arbitrary. So you can have any value within greater than 0, greater or equal to 0. So this is interesting. This is because of your engineering perspective, basically. You can choose any value, and based on that, you can have different solutions. So infinite number of solutions is possible based on the values of the mu that you're choosing, and it has to be based on your system's requirement ultimately. So probably we'll start solving the problem with assuming one arbitrary value of mu, but from designer to designer, it will be different. And what about the R? R is not given, but we can always find it from here. R is basically 1. R matrix is, you can write 1 because it is x squared. So you can write it in terms of how it is 1, because you can write is U square is given. So you can write in this way, U transpose R U. So it can be 1 with another. So this is a single value. Transpose doesn't make any difference. So ultimately it will be U transpose U. So we can write it U square. So from that we can figure it out that our R is basically 1. So we figure out the value of Q, we figure out the value of R, we figure out the value of A, and we figure out the value of B. Now our target is to figure out what should be the value of P. And once we have the value of the P figured out, then P will be figured out from reduced matrix Ricardi equation. So once the P is figured out, then we find out the value of the K, gain matrix K. So reduced Ricardi equation. The solution starts now after getting all these values from the question. Then your reduced Ricardi equation is A star P plus P A minus PB R inverse. R inverse is basically 1 inverse is same as 1. Then we have B star. Star is actually a complex conjugate. So our for a real matrix, it is same as transpose. So as we have explained in the last class, then we have P, and then we have Q equal to 0. So now we have our A matrix. A matrix is simply 0. Okay, so A transpose will be required first. So, or then you can write the A matrix, then make it transpose of it. So what is our A matrix? 0. Our A matrix is basically 0, 1, 0, 0. So you can write it row wise, and it will be 0, 0, 1, 0. So we're taking transpose of the A matrix, it will be 0, 0, 1, 0. Then you have phi matrix, which is yet to be figured out, but we can have 4 components because the matrix dimension has to be matched. So we can assume that it will be 1, 1, E 1, 2, and 1. Since it is a symmetrical matrix, 2, 1 will be also same as 1, 2, and then 2, 2. And then P 1, 1, P 1, 2, P 1, 2, P 2, 2. And your A matrix 0, 1, 0, 0 minus again your P matrix E11, E12, E12, E2. There you have your P matrix that is 0, 1. Then you have R matrix, which is simply 1. R inverse is same as R, unless otherwise it is a multidimensional matrix. You can keep it like that. And then B transpose is 0, 1. Since it is a real matrix, so complex conjugate is same as transpose. And then finally, you will have your P matrix coming again, 1, 0. Sorry, P11, P12, P12. Finally, you will have your Q matrix. Q matrix is given, so 1, 0, 0, and that should be equal to 0. So basically, all other component is to be 0. Okay, so now we have to solve this one ultimately, and then we have to figure out the equations. And based on those equations, we have to figure out the values of E1, 1, E1, 2, and P2, 2. So let's multiply these values and then figure out what we can obtain. So multiplying this one and this one, basically the first, this one will be multiplied by this one. So ultimately it will be 0, since multiplying with 0. Then this one will be multiplied by this one, and also it will be 0. And this one will be multiplied by this one. So ultimately the first one will be available. So this will be P11, and this one multiplying with this one, first one is available, so P12. So it's simplified, first component. Then second component will be starting with multiplying this two. Okay, so multiply this one and this one. So ultimately, what you're going to get is this one is getting multiplied with this one. So 0 is coming. Okay, so 0. Then this one is multiplied with this one. So ultimately, the first parameter will be there. So P11 will be available. P11. Okay, similarly, this one multiplied with this one will give you 0. This one multiplied with this one will give you E12. So this is your second component. And then you have these two multiplying together. So basically multiplying this one multiplying with this one. So P12 will be available. P12 and this one multiplying with this one, basically P22 will be available. Okay, so P22 is available now. And it will be further multiplied by 1. And also we can simplify this one. So this one will be becoming, and this will be a row matrix, so basically. So this will become P12 and P22. So next is keep the Q matrix as it is for now, 1, 0, 0 mu, and that should be equal to 0, 0, all 0. Okay, so next is this matrix is not hurting us much basically. So this will be simply as it is. And we can add this 2 as well. So adding these 2 is first derivative is 0, second derivative is this one is P11. This is P11 as well. And there will be 2 P12. So calculation is not complicated, but it's slightly lengthy and you have to wait how to figure it out. So now you have to multiply this one. Okay, so we can just omit the 1 value because of the fact is that it will keep the same magnitude. So P11 and P12 will be multiplied. So P11, sorry, P11 and P1 multiplied. So P12 square, then you'll have P12, P22. Then you'll have same because they become identical, say P12, P22, and P22 square. With that, you have 1, 0, 0 mu. So all this will be simply added or subtracted, and then it will be equating with the all 0 values. So now let's final addition gives us the first parameter of all the matrices will be becoming is 1 minus P12 square. The second parameter is P11 minus P11 minus P12, P22. Third parameter is P11 minus, it generally it becomes identical. So P12, P22. Then you'll have 2P12 minus 2 P22 square plus. So this should be equal to your other side, that is all 0. So now from this we can find out 3 equation. 3 unknowns there, P11, P12, and P22. So for 3 unknown, we need 3 equation, and we can easily figure it out. What are these 3 equations? So basically 1 minus P12 square equal to 0. That gives us straight away P12 is basically 1. Similarly, the second equation is P11 minus P12, P22 equal to 0. And that gives us, since P11 is 1, we can easily, it's P12 is 1, so you can easily write that this one is 1. So you can easily write that P11 will be equal to P22. And also it is a fact because we know that uh, P1, 2 and P2 1 will be same value, but these two showing the same value may have different value, but in this case, we have seen that P1 and P2 is also having same value. So the third equation, that is 2 P1 2 plus minus P2 square plus mu equal to 0. So we are interested about figuring out what should be the mu value, and based on the mu value, what should be the value of P22. So basically, we can easily write that you can take the P22 in the other side and then simplify that. So P22 is simply will become mu plus 2 into P1, 2 is 1, so mu plus 2 plus mu plus 2. So simply your P22 is becoming square root of mu plus 2. And as P1 is same as P22, we can write that P11 is also having same value. So the matrix that we are looking for is P matrix, which is simply P11, P12, P21, which is also P12, is P22 is becoming square root of mu plus 2, 1, 1, square root of mu plus 2. Okay, so once you have your P matrix obtained, and value of the mu, as you know, that can be any value equal or greater than 0. So you can choose any value in between. So, but keep it uh, with the formulas now. And so what will be our next time after figuring out P? We should look for what is optimal feedback gain K. So optimal feedback gain K. So according to the formula, K is R inverse E transpose P. So R inverse basically R inverse B transpose P. So R is 1, nothing to worry about. R P transpose is 0, 1. And P, we already figure out that is P11, P12, P12, P22. And we can replace. After computing, you can see that the first it will become a row matrix eventually. So ultimately, it will be P12 and P22. Okay, so and we know the values of the P1 is 1 and P2 is mu square root of mu plus 2. So we can say that this is also our K1 and K2. So to feedback, we started with in the diagram, as you can see here. So this is your X1. So corresponding to the X1, you will have K1, and corresponding to the X2, you will have K2, which is also inside this one. So they have symbolically shown 1, but inside those we have both K1 and K2. So we already figured out the value of K1 and K2, which is 1 and square root of mu plus 2. So now what should be our control signal, optimal control signal? So optimal control signal, we're looking for U. So ut is simply minus k x t. So ultimately minus k x k1, k2, and x1, x2. So it will give us minus k1 x1 minus k2 x2. So k1 is simply 1, so you can write minus x1 and minus square root of mu plus 2 x2. Okay, so now we can figure out what should be the characteristic equation as well, because we have all the values figured out. So the characteristic equation of the solution, characteristic equation of the system, characteristic equation, because we already figured out the K matrix. So we know that our characteristic equation is given by SI minus A minus BK. So you have to find out the determinant of this one. So that will give us the characteristic equation of the system. We want to check whether the system is stable or not. Okay, so how can we do that? So just figure out all the values. We know that this will be S0, 0, S times the identity matrix. Then you have minus A matrix, that is 0, 1, 0, 0. And we can take a bigger square there. So minus A minus B, B is basically 0, 1, 0, 1. Previously, we have also done that, so it's nothing K1, K2. You don't have to do it as I'm doing it. I'm just doing for your ease of understanding whether you will call that or not for that. But we already know what should be the value here from our previous knowledge. So S0, 0, S. Then you'll have 0. This will be simply nothing but 0, 0K1, 0K2, column wise. So we can just subtract that. So ultimately it will give us minus 0, 1, and then you'll have minus K1 minus K2. Okay, so finally, what we are going to get is S minus 1, it will be plus K1, S plus K2. Okay, so find the determinant of that. Ultimately, it will give you S multiplied with S plus K2 plus K1. So S square plus K2S plus K1. And we know the values of K1 and K2. So ultimately, S square plus square root of mu plus 2S plus 1. And we have to, the characteristic equation is simply S square plus mu plus 2S plus 1 equal to 0. Now this will give us two roots. And as you know, that we have a choice of mu, so you can have any value greater or equal to 0. So arbitrarily say mu equal to 1, which is equal to 1, then it's becoming S square plus square root of 3S plus 1 equal to 0. You can also take mu equal to 2, then it will be square root of 2. You can take mu equal to 2, then it will be 2S. So in that case, it will be S square plus twice S plus 1. So you can have a square formula. So it's up to you, whatever you prefer. I'm just keeping with same value with the book that they have taken. So minus B plus minus root over B square minus 4 C by twice A, which is simply 2 times 1. So ultimately what we are going to get is minus square root of 3 by 2 plus minus j half. So one pole, our poles are becoming basically minus 0.866 plus minus j 0.5. So in the S plane, basically minus 0.5 somewhere here, then minus, sorry, minus 0.866. But the real part is negative. So our system is stable and somewhere 0.5, somewhere here maybe minus and plus 0.5. So the pole locations are there. So this indicates that our design system gives a stable condition. Similarly, you can experiment with some other values of mu for what the system becomes. So sometimes this is a oscillatory your damped, underdamped solution, but you can also have critically damped or over damped. Or okay, so those are also possible based on the different values of p. So this is the end of your problems, but nowadays these problems are actually solved with your computer programs. These lengthy programs then becomes a lot easier nowadays.